Hello, it's Dr. Daystorms once again, and today in this presentation we're going to be discussing atomic numbers and mass numbers, and also just going over the symbols for the elements. So the chemical symbol is where it's usually a one or two letter symbol for the element itself. The first letter is always capitalized, and if there's more than one letter, then those additional letters are not capitalized. They're lowercase. Okay? I say that most are symbolized by one or two letters because there are a handful that do not have their official names yet, and so they have 3 letters. They are really high in atomic number. So the example that we're going to use here for right now is carbon. So carbon's symbol is a capital C. And that's it. Right? Now, if you notice, there's something called the atomic number. The atomic number, which is sometimes denoted with the letter Z or Z, it is equal to the number of protons in the element. Okay, now if it's an element, that means it's going to have the same number of protons and the same number of electrons because it's overall neutral. Now we're going to find out that it is possible for an atom to either gain or lose electrons, but it's no longer going to have the same number of protons and electrons because it will be charged, either positively charged or negatively charged. But right now, we're going to say that the atomic number, it really is equal to the number of protons, because if an atom gains or would gain or lose a proton, that would no longer be the same element. It would be a different element and have different properties. So the atomic number is the number of protons, and if it's neutral, it's also the number of electrons. It is always the lower number of the two that's usually given on the periodic table. Whereas the mass number is actually the number of protons plus the number of neutrons. So it's always the larger number of the numbers given on the periodic table. Both of these, both the atomic number and the mass number, are integers. They must be whole numbers. You can't have half of a neutron or half of a proton. So they have to be whole numbers. That's very important. So the mass of an atom is given into atomic mass units, since we're talking about such small numbers, okay? Remember, it's like, these would be on the orders of magnitude of 10 to the minus 24, or 10 to the minus 23 grams. And that's not useful to talk about those in such ridiculously small numbers, so we use an AMU. And 1 proton and 1 neutron are both equal to approximately 1 AMU. Whereas an electron we don't even include in the configuration and trying to determine the mass of an atom, because it's 1/1800th the mass of a proton. And so that's why there's no way to have enough electrons in order for them to significantly affect the mass of an atom. Now, it is possible for atoms to be of the same element but have different masses. So if we look at this example here, with carbon, there are 4 different possible masses for a carbon atom to have. They are all going to have 6 as an atomic number, because they all have 6 protons. But if you notice, the mass number for each of these changes. We have 11, 12, 13, and 14. So what does that mean? What does that indicate? Well, once again, we already know that this here, the larger number, is the mass number. So what you do is you take the mass number, 11, minus the 6. That's going to give you the number of neutrons. So the C11, or carbon 11, has 5 neutrons. Carbon 12 has 6. Carbon 13 has 7. And carbon 14 has 8 possible. Or not 8 possible, it has 8 neutrons. But these are called isotopes. Don't get this confused with radioactive isotopes or radioactivity, because, remember, not all isotopes are radioactive. Radioactivity means that the atom naturally will emit a particle or a subparticle. So, if you look at most periodic tables, many times you'll see 3 numbers. So, for example, a periodic table may say something like O, which is oxygen, and it may have 16, 8, and then also say something like 15.998, something like that. Well, if you notice, the 1 number is not a whole number. Okay? So, almost always in the real world, we don't use a single atom or a single molecule. We use large quantities. And since there are these isotopes, and each of these isotopes can weigh a slightly different amount, what we do is we just take the average mass in calculation. So the number that's usually very similar in magnitude to the mass number, but it's not a whole number, that's the average atomic mass for that element. So if you notice, for oxygen, we have a mass number maybe 16, atomic number 8, but it's got an average atomic mass of 15.99998 or something. It's roughly 16.0. But that tells you that there are some oxygen atoms out there that weigh less than 16 AMUs. So let's just work an example here. Alright, this is taken from an older book, but says that naturally occurring chlorine is 75.78% Cl35, which has an atomic mass of 34.969 AMU, and 24.22% of all chlorines are of the 37 mass number, which has an atomic mass of 36.966 AMU. Calculate the average atomic mass, that is the atomic weight, of chlorine. So, since percent we can just say is, well, sorry about that, don't want to give away the answer. Since percent is the same thing as saying 0.7578 times 34.969 plus 0.2422 times the one for 37, which is 36.966 AMU. What will that equal? If you do this math, you're going to come up with the number 35.4526, depending upon rounding, which if we want to go to significant figures based off of this calculation here, we're going to go to how many significant figures? We're going to go to 4 significant figures, because that's the one in multiplication and division. It's the one that has the lowest. There's 4 there and 4 there. So therefore, we would be rounding this to a final answer of 35.45 AMU. Don't forget your units. Hopefully this has helped you in learning the difference between the mass number, the atomic number, and the average atomic mass, or also known as the atomic weight of an element.